So the answer is 13. And the reason for this is quite interesting. If you look at the answers we were getting so far, this is the number of calls for each number. So when we had Fibbo 36, the number of calls was 1. When the input was 35, the number of calls was also 1. When the input was 34, the number of calls was 2. When the input was 33, the number of calls was 3. When the input was 32, the number of calls was 5. We should start to notice a pattern. This is exactly the Fibonacci series that we're computing here. Every time we decrease n by 1, so to get the number of calls for 32, we added the number of calls for 1 before and the number of calls for 2 before. And if you look at the structure of this, it follows from the same rule that we had, thinking about the number of rabbits reproducing, that every one that we have on the previous level leads to 2 more. And that means as we do this addition, we have all the previous calls. So we had 1 call to 34 at the previous level. We're going to produce 2 new calls, but the inputs are different. But if we look at the way the inputs are distributed, we have 2 plus 1 here. We have 1 plus 1 for 34. We have 2 plus 1 for 33. For 32, we have 2 plus 3. We have 5. For 31, we're going to have 8 calls. And for 30, we're going to have 5 plus 8, which is 13. And this will keep going. These numbers will get quite big very fast. And the number of calls that we need every time we evaluate Fibbo 36. So to evaluate the number of calls when we started with 36, that's going to be the result of Fibbo of 36 minus n minus 1. So the number of calls we'll need to Fibbo 2 in evaluating Fibbo 36 will be Fibbo 33 call. And we don't know what that number is yet, because when we tried to evaluate Fibonacci 36 using our recursive definition, our evaluator timed out. So we're in big trouble. If we want to figure out how many calls there are, we need a more efficient way of computing Fibonacci numbers. So let's see if we can do that. And the reason this was so inefficient is because we're doing all this redundant work, right? We saw that to compute Fibonacci 36, well, we had to compute Fibonacci 35, and we had to compute Fibonacci 34. All of this work computing Fibonacci 34, we did the same exact thing over here, right? This is producing the same output. There's tons and tons of redundant computation going on. So if we're going to compute this more efficiently, we don't want to duplicate all that work. We need to do it in a way where we don't need to keep recomputing the same thing. So the solution to this is, instead of using a recursive procedure to compute Fibonacci, we're going to compute Fibonacci using a while loop. Anything that we can define recursively, we can also define without using a recursive definition. It's often much easier and cleaner to think about things with the recursive definition, but it's often not the fastest way to calculate things. And certainly in this case, because of all the redundant computation, it's a very, very inefficient way to calculate Fibonacci. So let's try to do this with a while loop instead, and we'll make that a quiz.